All right, thank you for joining us today in the seventh episode of the Journal Club of Clinical AI Academy. Today's actually mark a very interesting and very step forward. This is the first guest lecture of the Clinical AI Academy Journal Club. Today we have the title Differences Between Man and Machine: How People Are Not Machines and Machines Can Never Be People by David Hsing, who's coming from an engineering background, and he'll tell us about himself a little bit. So, welcome, David.
Okay. Pleasure.
And at Clinic AI Academy, we aim to build AI literacy specifically for healthcare by providing high quality, open source educational transdisciplinary content focused on AI, neuroscience, medicine, psychology, philosophy, linguistics, and more. We invite you to join our open discussions, shared exploration, and reflective practice. Everyone with an interest in AI and medicine is more than welcome to join us, regardless of your background or profession. We're trying to kind of break the boundaries and welcome you to join our community. A very warm welcome to you, David, and many thanks, as I said before and now, for joining us today. We're really glad to have you, and please go ahead, tell us about yourself and share your screen, and let's start with the talk.
Hi, my name is David Hsing. I worked at Intel as a microprocessor circuit layout designer for over 20 years. Recently, in the last couple of years, I've transitioned into a project management role, taking care of design software tool releases. My topic is the differences between man and machine, how people are not machines and machine can never be people. AI personhood was banned by UN in 2021 in its recommendation on ethics of artificial intelligence in 2021. It says member states should, in particular, take into account that ultimate responsibility and accountability must always lie with natural or legal persons. That AI systems should not be given legal personalities themselves. It means that, companies could be people, could be considered people in legal circumstances, and people, of course, could be people, but not machines. They, this agreement basically says it's unethical to consider a machine to be a person. So, what exactly are the differences between man and machine now and forever? And emphasis on forever, not just now. And the thing is, people are alive and machines aren't. And there's some basic criteria of all living beings that include but not limited to reproduction, like the ability to pass genetic information onto an offspring, respiration, the chemical reactions that release energy from food. That means this living entity can make their own energy and not just rely on fuel or something. Homeostasis, the ability of the organization to maintain a stable internal environment, which is, different from what viruses couldn't do. Viruses, they can't perform this homeostasis. They have to rely on manipulating their surroundings to do that, to compensate for this lack of homeostasis. And living things, they grow. Unlike machines, living things are grown as integrated wholes, and they're not assembled from manufactured parts. So if you have a living being, you can't disassemble it. They're not put together with parts. If you disassemble it, for example, you can't like detach skin and flesh from bone just like that without doing any damage. You actually have to cut something, and you will inevitably damage something. So people may ask, what about xenobots, those so-called living machines that's made with stem cells? Well, they don't have real reproduction. They just scoop up piles of cells. And then each so-called generations, they're not real generations because the next waves of these reproduction, those so-called, reproduction, but not real reproduction, they get smaller and smaller until they can't reproduce anymore. They're basically smaller copies and not really reproduction. And then they don't have respiration. They have to be supplied with just fuel. They don't have They don't generate energy on their own. They do perform homeostasis. They're able to self-repair. And then again, they can't grow. They're not growing. They're just assembled. And there's no cell division. So no, robots are they're called living machines, but they don't qualify as being alive. So one may wonder, all we got to do is work all the science of life into the machines to obtain a living being, right? Well, no. The fundamental nature of a machine is completely different from any living being, despite any appearance. I mean, you can look like a living thing, but you can't be a living thing. The thing is, machines are artifacts. They are designed, they are assembled, they are manufactured, and they are designed to transmit forces and motion and energy from one part to another in a predetermined manner. So that's basically a dictionary definition of what a machine is. Living beings that are made, they're not manufacturers. You were born, they're not constructed. And then you say random number generators, they don't disrupt the predetermination because they function as noise generators. And machines, they contain design. I mean, you're not designed, you just evolve. In the process of evolution, it's not one of design. And as a result of this design, this machine doesn't possess any agency. They don't do anything by themselves. I'll explain how this is in a minute. Let's take a doorknob, for example. Now, when I turn a doorknob, obviously that doorknob isn't turning by itself. So I'm telling it what to do. I mean, in fact, I'm just directly grabbing it and turning it. So it doesn't matter if I put a little computer in it. It doesn't matter if I put some sensor in it connected to some detector or anything else, some actuators. It's still responding to command. It doesn't have a mind of its own. And that's the point. That is a major thing. So unlike a person, a machine doesn't have a mind. It could never have one. And why? Why can't it have one? Because it's an artifact. In order to have a machine, you have to make one. Now, there's a lot of different arguments out there that kind of ignore this major point. You have to make a machine. And unlike a little, I mean, there's a lot of different philosophical arguments that kind of ignore it by it's basically saying, oh, you have a bunch of functions, and then if it works, it works. And if you can duplicate it, it works. But it kind of ignored the process of making a machine. I mean, you have to design one, right? And if you have to design one, then you have a problem because if you design, you're having it follow a command, a structure of what it's supposed to do, like what I said earlier about the doorknob. And if you're gonna get rid of that, you're trying to get rid of this command function, then you're basically saying you're going to design without a design. You say, oh, well, I'm gonna design something that doesn't follow anything. That's a contradiction. So it's basically the concept of this machine doing something of any artifact that's doing something by itself, quote unquote, it's wishful thinking. It's good science fiction, but it's not engineering reality. Just by virtue of something being engineered. I mean, you engineer something that's not being engineered. That doesn't make any sense. And many people doesn't like that when I tell them that. So they have their due point to some counter arguments. There's two major ones. First, they said, well, there are evolutionary algorithms. So that's what they're called. But this is sort of a misnomer. It says it says it's evolutionary, but it's still programmed. It's still in algorithm. It's still an algorithm, right? Is still a design. So this design is still producing a design. This is still a product of design. So it's not something that's free of design. And the second is having to do with all the rage on nowadays, neural networks. Now, if they say, oh, we have NNs, they so-called learn from the data, they supposedly make decisions themselves. Well, no, that's not how it works. Now, neural networks is still built with algorithms, just like before. It's still algorithmic because It just looks like it's doing something by itself. It looks like it has agency, but it doesn't. The algorithm is takes all the data, the training data. Like I don't really like calling it training data because it's almost like treating it as a person. I would I like calling it like have data conditioning. And then this network that's conditioned with the data responds to the way it's programmed. Like the network itself is programmed. So you put all those conditioning data in, you get the behavior out. That is a designed behavior of the neural net. So this machine learning and this term itself is not actually referring to real learning because in some AI textbook already admitted to this. Like like for example, this P. Mitchell machine learning from 1997. It says, for example, a database system allows users to update data entry with fit our definition of a learning system, improve performance by answering database queries based on experience gained from database updates. Now, if you take a look at this carefully, even something like a spreadsheet qualifies, right? It you fill in a spreadsheet with some entries. That's inputting data. They say a so-called experience gain. That's another specific technical term that they put in, but it's not real experience. It's a data entry thing. And then this is not real learning. This is not experience. And then it's not. I mean, if even a spreadsheet qualifies as learning, then it's simply just not learning. It's data acquisition and data processing. It's not learning. Now, the difference is people deal with meaning. Machines don't deal with meaning. We do. And machines can't deal with meaning. They can't ever deal with meaning based on how they work. Now, remember the definition earlier. The machine is assembly of manufactured parts that transmit motion, energy from one part to another to do work. Now, this is an illustration, a simple illustration of loads moving through the system through 5 steps. It just loads go through here, here, here. It fills up. It goes from one, it transfer load from one to another, and then at the end you just have these store loads, these store sequences. This is what a machine sees. These values, like a white box, represent like a low load, and yellow box represent a high load. It would be 0, 0, 0, 0, 1. It would be like if it's a binary, then it's 0, 0, 0, 0, 1. And these ones and zeros just move through the system. This high and low just move through the system until over here, if you read it at step 5, it's 1, 0, 1, 1, 0. So that's the value. And this is what a machine sees. It's just a bunch of loads inside the system. It's not seeing anything else. Now let's perform a uh, thought experiment based on what that example I had back there. Now imagine that you're a machine. You just see a bunch of loads moving through you. And those loads, it can represent anything. But here you can have those high and low loads to represent shapes. And you memorize a whole bunch of shapes. Then you memorize the order the shapes are supposed to go in. So if you see a bunch of shapes in a certain order, you would respond. You would respond to these loads by picking another load, in another prescribed order. Now, just from that, did you just learn any meaning behind any language? No, I mean you just see a bunch of loads, right? You see high low, you see one load coming under after another. You see a bunch of sequences, but those sequences don't mean anything other than one thing coming up after another. That doesn't mean anything, and that's what all every machine sees. They're just a bunch of pulses that they're signal pulses, and they're images on whether images from cameras or they're they're from input any kind of other inputs, the sounds of microphones or anything else. It's just bunch of highs and lows, high loads, low loads. And what was on the previous slide was illustration of what a machine algorithm is and how it works. I mean, this is how it works. It just even at the most basic level, that's what a machine does. If you go down to just a little one single transistor, it's just a gate. Right? It's just an input and then a gate and an output. You have this signal that goes through, and it's just a gate that's either stops the signal or lets it go through. It's just a bunch of loads. It just treats a bunch of loads as it doesn't really see anything but those loads. And that's what that's what anything that's what all these machines sees. Its entire world is these sequences. It doesn't know anything outside of itself other than these sequences. It is no such world outside of itself. There's no such thing. Its entire world is this. It's just this. It's high, low, low, low. That's it. That's the entire world. Because I mean, you can give it more and more sensors. You can give it programming. You can program it to death. It would still be the same thing. It would just be more and more of this. You can expand this. You can have millions and billions of instructions, millions and billions of loads. At the fundamental level, it will still just be the same. It would just be this. No meaning. Just one thing coming after another. That's it. So if if that's the way it is, then how can any machine work then? How does any program deal with the world? Well, they work because their output behavior is good enough to deal with the world correctly up to a certain point. I mean, if the program works, I mean, you see it as working, but it doesn't mean that it's handling meaning. It only means it's dealing with the world correctly according to how you programmed it. So now I have a very simple pseudocode example here. Let P equals night, input R. If R equals day, then print P is R. Now, if I type day, then the output would be night is day. Yeah, that's correct output because according to this piece of code right here, night is day is the correct output. It doesn't make sense to you, but that's the programming. I mean, the machine follows the programming, even though it might, regardless of whether it conforms to external reality or not. It doesn't matter because that's the programming. Now, it doesn't, if it works, it's a good enough design. If not, it's flawed, right? It's bad design. If something works the way everyone expects, it's a feature. If it's not, it's a bug that needs fixing. If it's not working expected, but in a good way, then it's an old joke, right? It's not a bug, it's a feature. Now, there's some consequences of not dealing with meaning. Let's start with the left. This is a deep learning algorithm of trying to identify the road vehicles in a 3D simulation. You see, they have a typical stance of this typically simulated stance of a bus. Yes, it can recognize a bus if it's just some typical stance, but as soon as you move it away from what it's seeing in its training, then it won't recognize it anymore. It just says, oh, it's a garbage truck, it's a punching bag, a snowplow, and anything but a school bus. Because in the training, if the training data doesn't, it's not, it doesn't, it always has these things it's planted on the ground. As soon as it's not something that's the data set's not handling, then well, when it's out of bounds, it could be anything. It could be identified as anything. So goes with the motor scooter, which ends up being identified as parachute, a bobsled, a parachute. I guess it likes parachute more than a bobsled. And then a fire truck, as soon as it leaves the ground, it gets identified as a school bus, fireboat, or bobsled. It really likes bobsleds and parachutes, I guess. Now, this is a study done, I think, by MIT, where they fed data of Earth's orbit around the sun into a model. Now this is the real orbit, the 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 real orbit and real model data, and this is supposed the real law that they extracted the law that's if when they extract the law behind the model, it's supposed to match this real true force law here from this real orbit. But what they found was they have this the law that they extracted from the model from this perfectly predicting this perfect orbit. The model, what happened was the model predicted the correct orbit. It predicted a circular orbit, but the forces of acting upon this Earth object is all over the place. It's some weird formula. It has nothing to do with the real force, the true force law. It's all over the place. I mean, this is nothing to do with real physics. However, it predicts it predicted this circular orbit here. So it only has this appearance of this prediction of physical law without the substance of any of it. Now come down here. This is a similar case to it's a more recent case than the ones on the left, but it's similar idea. It's when you have a panda, a picture of a panda, and they inserted this noise. This noise is a special calculated noise that's designed to confuse it. I mean, it's just this. When you look at it, it doesn't look like anything, right? But this thing, when this noise is added to this panda, is it produces a prediction, this final image, a prediction that says it's even more confident that this new image that it's a given than the normal the original image was a panda. I mean, it was the original prediction of a panda was only 57.7% confident that it was a panda, but the prediction of this new image with this noise added is a given with 99.3% confidence. So I mean, it's from this we can also deduce another thing. These neural networks, they're not actually referring to anything at all. They're not referring to actual any concept. Because look at this. I mean, one is panda, right? I mean, normally we look at a panda as just a panda. I mean, experience, we look at this thing, it's a panda. We look at this in another picture on the right, but it's the same, right? It's a panda. But if a neural network model is actually um, referring to what a image is, what is actually referring to, then this should be it should be the same identification whether there's some little noise added or not. I mean, our eyes don't even tell the difference. I mean, this is a panda, that's a panda. I mean, we take a look at it. Of course, it's a panda, but to a machine, as soon as you stick some stuff in it turns into something utterly different. So it's not really identifying any panda. I mean, there's some studies done that's saying that it's not really identifying any shapes. Okay, it's not identifying. Oh, it's a head, it's a whatever. It's identifying whatever pixels that are in there, whatever patterns that happens to be in there, even if this is the sky, even if it's the tree, some parts of the trunk, and identify that as quote unquote panda or cow or anything. That's why some certain pictures that some other examples out there that says, well, if there's a lot of cows that have like there's more picture with cows with a blue sky, and for example, there's more picture with cows that happens to have the blue sky than anything else, then it would identify anything has more blue sky in it as a cow instead of anything else. I mean, it's not really identifying anything. It's only identifying the most prevalent matching pattern. It's not, that's a huge problem right there. So, and we can also ask sort of the opposite question. Now, how can we deal with the world? A machine can do it. How can we deal with it? Well, unlike machines, we have minds. We possess consciousness and intentionality. Now, this word is a special word in the philosophy of mind. That means the power of minds and mental states to be about, represent, or to stand for things, properties, and states of affairs. And in addition, we're not information processors like machines are, like that couple slides back when I talked about spreadsheet. We're not just information processors. Right? We're not just filling in blanks or filling in information, filling in numbers there. We're actually experiencing the world. And this conscious experience is actually producing new information instead of just processing information. And in addition to that, our brains are completely dynamic. They don't have fixed states like the machines do. Now, take away from this and some parting thoughts. Do you know that color has no reality outside your body? Yeah. Color is something that exists completely inside your head. It's just something in your head. Color is a sensation, just like smell, touch, hearing. It's caused by physical reality, but it doesn't have any physical reality of its own. It's not outside of your body. And this is the hard part. Color is not a property of the thing that's causing the sensation. In other words, grass is not green, sky is not blue. Rather, they have physical properties that make you perceive green and blue, but that's only true in some circumstances. I mean, it's easier to understand this concept if you think about it in terms of you touching, or someone touching you. If somebody touch you on the arm, you feel the touch, and the feeling is caused by the physical reality of the finger or whatever is touching your skin. But it wouldn't occur to you to think of the feeling as a property of the other person's finger, and it wouldn't. I mean, it's a sensation. It's a touching sensation. Now, this is a good example. And what is the color of this dress? I mean, this is an internet sensation. You can look at this up. You can look this up. The dress in Wikipedia. This caused an uproar a couple of years back, and a lot of people say, oh, it can only be white and gold. That's the color. Then it must be white and gold. Must be a white and gold dress. Half of the people says white and gold dress. Other half people dress says it's blue and black. Which one is it? I mean, but it turns out its dress itself it's blue and black. But how you perceive it is up to an individual. There's some explanation in the Wikipedia. You can look it up, but it just shows how subjective color is. It's not something that's just a property. It's your conscious experience. Yeah. I've that's end of my talk right now.
Right. Okay. Thank you so much for this. I mean, fantastic talk. Honestly, I really enjoyed it. And you have a realistic way of looking at it, I guess, from an engineering point of view, away from the hype.
Yeah.
Um, I have questions, but apparently we don't have enough time to go through them. So you made an emphasis on living as a difference between us and machines, but then you kind of also made the statement that it does not matter if like yeah if at the end of the day the machine can do what we do, right? Then it really does not matter if it's conscious, if it's is utility more important than those philosophical questions.
Well, there's actually there's some consideration of like let me go back to it's also an ethical question because I mean there's some cases where corporations trying to shirk responsibility by saying, "Oh, the bot did it."
Right.
Like Air Canada had a case where it says, "Oh, our chatbot gave you information. Oh, it's the chatbot's fault. It's not the company's fault. It's the bot's fault." That's the argument they tried to make. They actually tried to say that. They tried to actually do that.
I see.
And
So you think that if you
uh,
just don't understand that the machines are just machines and they don't have meaning, or then you might end up with ethical dilemmas.
yeah.
Right. Um, and so just in 1 minute, if you had to say something for doctors out there, because that's what we're trying to do for clinical AI, what would your advice be from your perspective when a doctor learns about AI, just in 30 seconds?
Oh, well, from my perspective, you can't really completely trust. You must verify very carefully because I've heard there's actually one case where an emergency doctor tried ChatGPT and he found out that the ChatGPT says some dangerous stuff where because the doctor has a judgment and there's a lot of even the patient themselves might give some bad information that only a doctor can tell. And if you completely just rely upon ChatGPT or something like that, it it would just completely skip over this crucial uh, information that only doctor knows.
Right. Thank you so much.